All right, so this is chapter 8. This is Dynamics 2, Motion in a Plane. So you'll recall chapter 6 was Dynamics 1, Motion along a straight line. And then chapter 7 was Newton's third law. Well, now we have motion in a plane. So two dimensions, right? Okay, so we'll compute two-dimensional trajectories. Well, we've already done a little bit of that. To understand the dynamics, that means forces, of uniform circular motion. We've talked about circular motion before, but we'll just go into a little bit more depth. To learn the basic ideas of orbital motion, again, we've talked about that somewhat. And this is kind of fun. To answer, how does the water stay in the bucket in related questions? What's that? So take a bucket of water and do this, vertical circle. And if you get it at the right speed, the water won't fall out of the bucket. So there you go. All right. So let's review uniform circular motion. So you'll recall counterclockwise means omega is positive. Clockwise, the convention is omega is negative. Just a convention, but we're going to use it. Something else that we've had. Now, how many times have you seen this slide? So this is uniform circular motion. Uniform means that the speed is constant, but obviously the direction is changing. So we figured out the direction of the acceleration by doing the vector subtraction. And we used to call it A sub c, right? C stands for centripetal, which means center seeking. Now we're going to call it A sub r, radial. You can call it whatever you like, actually, but I'm going to call it A sub r. And we learned this earlier. A sub r is v squared over r, or if you use v equals r omega, it's omega squared r. So either one of these, just depends on the problem, what they're asking. Okay, so why are we switching from C to R on our subscripts? Well, because we're going to use a new coordinate system. So it's much easier when you're doing these circular motion problems to use what's called the RTZ, I call it RITS, the RITS coordinate system. So here's the RITS coordinate system. So again, the object is undergoing circular motion. So here's the object. So the object is actually the origin. That's kind of interesting, right? So the origin is going to be moving, right? That's kind of interesting. Okay, so since it's going in a circle, there's always so there's a radial piece, right? This is the radial axis, the r-axis, okay, the radial axis. Now, here's what's important. The r-axis, origin is the object. It points toward, the axis points towards the center of the circle. So positive direction is from the object towards the center of the circle. Always. I don't care where the object is. If the object is here, the r-axis points from the origin positive towards the center of the circle. So that's the radial axis. There's also something called a t-axis, tangential, right? If here's the object, that's this line here. This axis is tangent to this line, right? So there's the r-axis. That's the r. There's the t, tangential, and there's the z. The z is out of the page, right? We're not going to use z very often, but once in a while. All right, so z is out of the page. Okay, so r, t, z. Bingo. RITS. Okay, RITS coordinate system. Oh, yeah, I just said that, right? So plus towards the center of the circle, minus away from the center of the circle. Okay, here's a question for you. A ladybug sits at the outer edge of a merry-go-round that is turning and slowing down. So I would underline that, slowing down, right? At the instant shown in the figure, the radial component of the ladybug's acceleration is what? So pause your video and figure it out. Okay, so we're imposing this coordinate system on this disk. And the question is the radial component of the acceleration. Well, the radial component always points towards the center of the circle. And so this points away from the center of the circle, so negative x would point towards the center of the circle. So the answer is 2, negative x, okay, towards the center of the circle. Here's another one, a ladybug one. A ladybug sits at the outer edge of a merry-go-round that is turning and slowing down. The tangential, okay, now the tangential, by the way, we didn't even care if it was slowing down, so I was wrong the last one. The tangential component of the ladybug's acceleration is what? Okay, now you care, right? Now it's important that it's slowing down. So we want to know that the tangential component of the acceleration. And you can see that this is the way the rotation is going, but it's slowing down. All right, so this is a good review question. You'll use what we learned a long time ago. Okay, so pause your video and figure it out. Okay, what did we learn if something is slowing down? Let's say that the velocity is that way, and if it's slowing down, the acceleration has to be opposite. Okay, so here, at this point, the velocity is tangent to the circle, right? So it's in the y direction. So what has to be true about the acceleration if it's slowing down? It has to be in the minus y direction. Agree? Again, just the velocity is always tangent to the circle, so the acceleration is opposite because it's slowing down, minus y. Okay, so let's talk about uniform circular motion, but now dynamics, so forces. We talked about kinematics a while ago, but now we need to talk about forces. So, okay, so just pretend I'm doing this, okay? So this is just a steel rod, maybe that high, on the tabletop. And this is a cylinder, and this is a string. So just pretend that, here's a tabletop with this metallic ring, and I have the little cylinder with a string, and I'm just kind of going like this, right? So the cylinder is going around and around, right? So this is what it looks like, right? Looking down on a tabletop. So you see that this disc, the cylinder just goes around and around and around, okay? And we're going to ignore friction. Ignore friction. So here's, right, so you're supposed to vote, okay? So you're supposed to choose which of these is correct. So number one, what are the forces on the block? Right, there's the picture, right? And again, this is happening on a horizontal tabletop. So what are the forces on the block? So pause your video and figure it out. Okay, so obviously there's going to be a normal force because it's on a tabletop. There's going to be weight. But what else is there going to be? What's making this? There's going to be a tension, right? There's going to be a tension. And what else? What else? That's it, right? Okay? All right, so that's all there is to it, The string is keeping it, right? The string is forcing it to go in a circle, okay? So, all right, okay? So it's not touching, it's not clear here, I guess. It's not touching this metal ring, all right? If it were touching the metal ring, there'd be a horizontal normal force. But it's not touching this metal ring. It's just going around on a tabletop, It's not touching, okay? So there's tension, there's normal force from the table, and there's weight. Okay, now by the way, what in the world is this? The force of motion. There's no such thing, right? If you're going to draw a force diagram, would you draw the force of motion? I don't think so. It's just no such thing, right? Okay, so there's tension from the string, normal from the table, weight from the earth. How do the two vertical forces compare? So, it's going along a horizontal plane, right? So how does the normal force compare to the weight? So pause your video and vote. Okay, hopefully you agree that they're equal and opposite, right? Because the cylinder's not going up and down, it just keeps going around in a circle. All right, so therefore, if the two vertical forces are equal and opposite, what has to be the net force? Well, vote, please. Pause your video and vote. Okay, obviously it's the tension, right? Because the normal cancels the weight. So the net force is the tension. Okay, what's the direction of that tension? Remember that the cylinder is going in a circle. So there has to be a acceleration pointed towards the center of the circle, and F equals ma. So if the acceleration points towards the center of the circle, the force has to point towards the center of the circle. So I just gave it away, right? So what's the direction of the net force? Towards the center of the circle. Okay, so therefore, there is a centripetal or a radial or a center-seeking acceleration, right? A radial or A centripetal equals v squared over r, or r omega squared. Again, you just choose this or this depending on the problem. And that equals the sum of the radial forces over m, right? Because F equals ma, or A equals F over m. Okay, so if there's a radial acceleration, there has to be at least one radial force. I'm going to put this on purpose because well, you'll see later on, but sometimes there are more than one radial force on the forces on the problem. So I just want to emphasize that. Okay, now here, okay, similar, but this time there's no string. So just imagine a table. I have this metal ring, which I'm going to use this time. I didn't really use it last time, right? So this time, I just take a ball and I kind of shoot it, push it, and it just kind of goes around and around, for a while until it slows down. Okay? So no string, right? All right. And we're going to ignore friction again, all right? So you just push the ball and it just kind of goes around and around. All right, same kind of questions. What are the forces on the ball? Well, there's the normal from the table, there's weight. But what else? What's keeping it from, if this were a piece of tissue paper or even something less dense, what would the ball do? Just break right through it, right? So isn't there a normal force that this metal ring exerts on the ball? Yeah, right? Remember, perpendicular to the surface, right? Okay. So what's the answer? Number 3, right? There's the normal force exerted by the metal hoop on the ball. There's a normal force that the tabletop exerts on the ball. And there's, of course, weight. Okay, what's the relationship between the normal force exerted by the table on the ball and the weight? Equal and opposite, because there's no acceleration in the vertical plane. So therefore, what's the net force? So pause and answer it. It should be obvious, right? It has to be the normal force that the hoop, the metal hoop or the metal ring exerts on the ball. All right? What's the direction of that net force? Well, you should know that by now, right? It's towards the center of the circle. Has to be. I think anything's going in a circle. Has to be an acceleration towards the center of the circle. Therefore, there has to be a force towards the center of the circle. F equals ma. So therefore, F equals ma, right? Or you can just say A equals F over m. So A equals the sum of the radial forces over m, and that equals this or that. And again, look at, this is only the radial or centripetal acceleration. That's why all I care about here are the radial forces. I don't care about anything else. I'm just saying if there's a radial or centripetal acceleration, there have to be radial forces. And that's all I care about, radial forces. You'll see more about that later. Okay, another example, one more. So here you have a satellite orbiting Earth. Now, what's the force or the forces that causes the satellite to orbit the Earth? Well, gravity, right? Gravity, no kidding. So what's the direction of the gravitational force that the Earth exerts on the satellite? Towards the center of the Earth. So this again, okay? All right, that again. Okay, so that's how we're going to do a lot of these problems. All right, so here's a problem. I'll do it. A block is placed on a turntable that rotates at a fixed angular velocity omega. So they give us omega, they give us mu s, they give us mu k, and they give us m, where I guess the m is the mass of the block. How far can the block be placed from the center of the turntable before it slips? All right, now, uniform circular motion problem, right? It's on a turntable. So we're going to use that Ritz coordinate system because it's going to make life easy for us. So here's this is what it would look like from above. So here's the turntable, and here's the block. And we want to know how far from the center of the turntable we can place the block before it starts slipping. In other words, we want it to be stationary relative to the turntable. Okay? All right, so that's what it would look like. But what we want to do now, of course, is draw the force diagram with our new Ritz coordinate system. So let's do it. Okay, so there's the turntable, the surface of the turntable, right? So this is our z-axis. And let's just say that the center of the turntable is this direction, you know. So say that's the r-axis. Remember, the r-axis always points from the object to the center of the circle. Okay, do we really need our t-axis? Nah. All we really need is our z and our radial. Okay, what are the forces acting on the block? Well, it's on a surface, so there's a normal force. As always. There's weight, as always. Now, what else is there? I mean, if this block were an ice cube, and if the turntable were an ice cube, would the ice cube go in a circle? Probably not, right? So there's friction, right? Now, it says how far can the block be placed from the center before it slips? So it's stationary, but but we want to put it as far away from the center as we can. So it's going to be Fs max. Agree? Fs max. All right, so here we have Fs max. And don't forget, this is the center of the circle, right? It wants to fly. It wants to fly off. It wants to fly away, right? So therefore, the frictional force has to be towards the center. I mean, it's just this, right? It's just that. There has to be a radial force. It's going in a circle. Has to be a radial force. What's the radial force? Fs max. Points towards the center of the circle. Radial force. Okay, so let's do it. So the sum of the z forces has to be 0, right? It's not accelerating up or down. So therefore, we know that the normal force equals the weight, right? This has to equal that. Okay, so that's old hat. That's nothing new. But now what we want to do, now we want to do the new part. Now we want to do the radial. Okay, now let's go back to this. So you notice that we can either use this equation we can either say, v squared over r or r omega squared. Now this problem, they give us the omega. So it stands to reason that we're probably going to want to use this, not that. Okay. All right, so I'll do it over here. I want more room. So the sum of the radial forces equals mr omega squared. Agree? I'm writing so you have to multiply everything by m. So multiply by m, sum of the forces will be mr omega squared. Okay. I could have said the sum of the radial forces equals mv squared over r, right? I could have said that. It would have been right, but it would have been dumb, because they give us omega. They don't give us v. So that would not have been smart. Okay, so look. This is always true for uniform circular motion, right? It's always true. There has to be a radial force to make it go in a circle. This is always true. All right, so that's great. But what's our job, though? Our job is to finish this equation. In other words, what are the radial forces in this setup? Well, okay, so I'm going to write it in a different color just to emphasize that this is always true. You always write it down, but then it's your job to figure out what the radial forces are. Now, since we've drawn the force diagram, it's a piece of cake, right? So the only radial force is Fs max. And we know what that is. Fs max is mu Sn, which is mu s, the weight, or, oops, mu s mg. Okay? All right. Now, what are we supposed to figure out? R. Okay, well, where's a R? There's a R. So I'm going to say this equals that. All right, so we have m r omega squared equals mu s mg. Now, what do you notice that cancels? The m's cancel, right? So goodbye, goodbye. Then we want to solve for r, so we divide by omega squared. And that's our answer. Let me write it nicely. So r equals mu sg over omega squared. And there you go. Okay. Again, maybe it's surprising to you, but you'll see it again and again. It does not depend on the mass of the block. What does it depend on? Of course, it depends on friction, right? I mean, if it's ice, it's going to be a pretty small radius. Agree? It also depends on the radial speed. I mean, if it's going really, 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 really fast, again, the radius is going to be pretty small, you know. Okay, so there you go. So that's kind of how you do it, right? You draw the force diagram, make sure that you have the radial forces pointing towards the center of the circle. If you need to do that, do that. You know, do the z-axis, and then write this, either sum of the forces equals mv squared over r or mROA squared. It's always going to be true, but then you have to figure out what the forces are, what the radial forces are, and then just solve it. Okay. Okay, now the next two examples, I usually try to find examples that aren't in the book, but these two examples are in the book. But I want to go over them because they're incredibly valuable. So I apologize a little bit. So we want to talk about making turns in a car. And first we're going to do an unbanked curve. So that just means you know the road is level. So you're just making a turn on a level road. And then we're going to do a banked turn. All right, that's all. Okay. All right, so here we go. We're driving a car, constant velocity, and we want to make a turn. So what are we going to do? Well, you know, remember, the car is the object, right? And so obviously the driver is going to turn the steering wheel, but who cares? There has to be an external force causing that car to make the turn. Agree? All right, so what is the external force? You know, when you're driving a car, you know, you turn the steering wheel, but what's the external force that causes that car to turn? It's friction, right? It's friction, okay? Agree? Static friction, hopefully. Have you ever tried to take a turn on ice? Doesn't work really well, okay? So it's static friction. Okay, so here are some beautiful pictures. So this is the top view, you know. Again, oh, by the way, we're making circular turns just to keep it easy, all right? Circular turns, because we want to, you know, use what we're learning about uniform circular motion. Okay, so the frictional force prevents the tire from slipping, right? Again, if you don't just think of driving on ice, you wouldn't have that force, so you wouldn't make the circle, right? You just go straight. Okay, so this is the top view. This is the rear view. Yeah. Again, this points towards us. I mean, you're going in a circle. Has to be a radial force. What's the only possible radial force? Friction, static friction, because you're not slipping, you're not sliding like on ice. So this points towards the center of the circle. Rear view points towards the center of the circle. Okay, draw the force diagram. Looks kind of familiar, huh? I mean, once again, normal, weight, friction, you know. It's the same diagram we just had, which was nice. Yeah. Okay, so, you know, I keep showing you this. That's okay. Just rubbing it in, right? All right, so this is what I want to do. All right, you are driving your car at constant velocity, approaching an unbanked curve. How fast can you drive your car and still make the turn before your tires begin to slip. So, if you're a traffic engineer and you're designing, highways or something like that, and you got to figure out the speed limit, you got to do some kind of analysis like this, right? So let's do it. Okay, so we already have the force diagram, so we know what to do. Okay, so the sum of the z forces equals 0. So once again, the normal force equals the weight. Okay? Now, we want to know the velocity, not the, and when they say the velocity, they mean v. If they want to know omega, they would say angular velocity. So we want to know v, so what would be smart? Well, we're going to say that the sum of the radial forces equals mv squared over r. Okay? Now, I'm going to keep repeating myself. This is always true, right? For circular motion, it's always true. So you just write it down, either this one or mr omega squared. But now it's your job, or our job, to complete it, right? To write down, okay, what are the radial forces? Now here, there's only one radial force, agree? Now look at, we want to go as fast as we can. So is this really Fs or Fs max? It's Fs max. So the radial force is just Fs max, which is mu Sn, which is mu Smg. Okay? So you just write this down because it's true, and then you have to figure out the rest depending on your individual problem. All right. Now what do we want to solve for? Velocity. So we're going to say this term equals that term. All right, so we have mv squared over r equals mu smg. What cancels? Well, we've already seen it. The mass cancels. So the mass cancels. And then we want to solve for v, so multiply both sides by r. Multiply both sides by r. Take the square root. That's it. So we'll call that V max, right? Because we use Fs max, So that's the fastest you can go and still make the turn. And again, it's independent of the mass, and it better be. Can you imagine trying to design a highway curve, and you have to have a speed limit for like a little Coupe car, then a different speed limit for like a Camaro, a different speed limit for a pickup truck, and then a different speed limit for like a big truck or something like that? It'd be insane, So independent of the mass. Now, it depends on friction. Well, no kidding, right? It better depend on friction. If the friction is really, really small, you got to go slow. Kind of makes sense, right? Okay, so, it just makes a lot of sense. Now, what happens if you exceed this velocity? You don't make the turn. If it's in the wintertime and you're in some place like Colorado, you end up in a snowbank. That's kind of how it is. Okay. Also notice, look at this. If the radius of the circle is really, really large, that means you're not really making much of a turn. You can go really, really fast. That kind of makes sense, right? That agrees with your experience. If it's a really tight turn, then you got to slow down, right? If r is small, you got to slow down. Okay, so this totally makes sense. Okay, now, if you've driven on highways, you've probably been on a banked curve before. And here's a picture of a banked curve, right? So it's not level. Now think about it. It costs a ton of money to make a banked curve because, I'm just going to, let's say this is the road right here. Well, you got to fill all this stuff with whatever, soil or whatnot. I'm just saying this is way more costly than making a level, unbanked curve. So why would they want to spend all that money? And I'm not talking about racetracks. I'm talking about on a highway. Why would they want to spend that kind of money to make a banked curve? There must be some benefit for it. So let's talk about banked curves. You see the bank curves, especially when there's not a whole lot of room to make a lot of highways, when you have a lot of space to make a really long R curve. Okay, so once again, we're driving our car. We want to make a turn. We're going to approach a banked curve. There has to be an external force on us, right? It has to be an external force. Because if there's not an external force, there's not going to be any change in motion. Okay, so here you go. So this is what it looks like, right? There's the curve, that's the road, some angle. That's the center of the circle. This is the top view. You know, we would go straight, except there's an external force acting on it, which we don't know what it is yet. Here's the center of the circle, right? Okay, we got to do the force diagram. Well, what are the forces? Well, obviously, you know, there's the weight. There's the normal, perpendicular to the surface, right? So there's the weight. Okay, here's the road. There's the normal. Is that it? Are there any other forces? No, that's it, right? No, okay, that's it. Now notice, what are we ignoring? We're ignoring friction. We're saying we're not even going to, we don't even need friction. That's the beauty of a banked curve, right? So no friction. Whoa. All right. So we have a normal force, normal to the road, and we have the weight. Now wait a second. I've said over and over and over again, if you're making a circle, there has to be a force pointing toward the center of the circle. There has to be a radial force. Well, all we have is this and this. Do either of these point towards the center of the circle? No. So what? Remember now, I mean, this is hopeless. This will never point. You know, this will never have a component that will point towards the center of a circle, right? But what about this guy? We can resolve that into components like we've done in the past. Let's do it. So this vector is the same as, you know, here's components. This is the z component. This is the r component. Well, this doesn't point towards the center of the circle, but this does. Agree? So this component of the normal force is the radial force. And again, this is the same thing as this, right? So if this is n cosine theta, this is n sine theta. So how do you like that? A component of the normal force is the radial force that makes the car go in a circle on a banked curve. All right? All right, so let's do it. You are driving a car at a constant velocity and approaching a banked curve. How fast can you drive your car and still make the turn before your tires begin to slip, right? You don't want to slide like on ice. Hint, use Newton's second law. No kidding. I mean, you got to admit, as soon as you see that force diagram, you got to use Newton's second law. What else would you do? All right, so here we go. Okay, so, I mean, it doesn't matter the order. So I've been doing the z first. Let me just do the z, okay? So the sum of the z forces is 0, agree? So that means, because it's not, you know, it's not accelerating up like this, right? So that means that this has to equal that. So this is n cosine theta. So sum of the z's equals 0. So n cos theta equals mg. Great. All right, now we do what we always do. Okay, so the sum, now let's see, we want velocity. We want a v, not an omega. So we say that the sum of the radial forces equals mv squared over r. Okay, now I know I'm sounding like I say the same thing over and over and over again. It's always true, so you write it down, okay? But now it's our job to say, okay, what is the sum of the radial forces? Well, there's only one radial force here. And what is it? It's this guy, which is this guy, which is just n sine theta. So it's n sine theta. Okay? Oh, great. Well, okay, now you can kind of do it however you want to do it. So I'll just show you how I do it, all right? Doesn't mean it's anything super fantastic. This is just the way I did it. Okay, so I look at these two. You know, I don't know what n is, right? I don't know what n is. So I kind of want to get rid of it. So, you know, you could just substitute for n and plug it in. Do whatever you want to do, but I'll just show you what I do. So I say n sine theta equals mv squared over r. Then I'm going to divide that by n cos theta so I can get rid of my n's. Then I'm going to divide this by n cos theta, but n cos theta equals mg, right? So it's same old, same old. So here the n's cancel, sine over cosine is tangent. So I have tangent theta. Okay, what cancels? The mass. Once again, we see that the mass cancels, right? So the mass cancels, goodbye. And then I just get v squared over rg, v squared over rg. I'm trying to solve for v, so therefore v equals rg tan theta square root of. And that's the answer. Now, once again, look at that crazy thing. What's important? You know, obviously the larger the r, the faster we can go, but look at, you know, it depends on the angle as well, right? Depends on the angle. But as I said before, no mass, but no sideways friction. No friction. So, you know, if you live in Colorado where they have a lot of snow, or somewhere where they have a lot of Utah where they have a lot of snow, this is incredibly safe, right? Making a bank turn, incredibly safe. You can have ice on the road. You can still make the turn, right? You can still make the turn. So it's incredibly wonderful. What happens if you go too fast? Well, then you're going to go up the bank. Not a good thing, right? Especially if there's a cliff on the other side. What if you go too slowly? Then you slide down the bank, okay? So anyway. And again, this is great because this doesn't include friction. Well, what if there is friction? Then that's another safety factor already built in, you know? So these are incredibly safe. Okay, so let's just kind of compare. For unbanked, we had V max was equal to square root of RGU sub S. This is max, right? And for a banked curve, we had V max was equal to square root of RG tan theta. So it's kind of like the mu s is sort of taken by the tan theta, right? Okay. So anyway, now you know what's so great about spending all that money to make a banked curve. All right, let's quit.